Hi, I'm Rick Bacon, Chief Executive of Aquametrology Systems. And this is a brief introduction into a major innovation in the technology for removing phosphate in wastewater treatment plants. So why do we need to address the problem of phosphates? Simply stated, they put the environment and human health at risk by enabling a process called eutrophication. And they do this by acting as a fertilizer that stimulates the growth of algae in lakes and rivers. And these algae consume the oxygen in these water resources on which many aquatic species depend, and they die as a consequence. Algae can also generate toxins that contaminate those water resources, so they cannot be used for drinking water supplies. A major source of phosphates are wastewater treatment plants, and there are regulations in place to oblige them to treat their effluent to remove those phosphates. Traditionally, wastewater treatment companies have had only two options for removing phosphates. They can either use bulk ferric salts in the form of ferric chloride or ferrous sulfate, or electrocoagulation. Both technologies have serious flaws, which is why we developed the SafeGuard H2O, a solution that is both more cost-effective and efficient. Ferric salts are produced by dissolving scrap metal in either a very strong acid or chlorine, and as a consequence, these reagents are extremely toxic and hazardous to handle and require specialist handling facilities and personnel to manage their use. In recent times, there have also been major issues around the security of supply of these reagents. And the fact that they are delivered in bulk by tanker has implications for the carbon footprint of this treatment process. Finally, there are major issues around the security of the quality of these reagents. This is a chemical analysis of ferric chloride supplied to a major utility in the US, and this is very typical. The reagent itself contains high levels of other impurities of concern, and is a consequence of the fact that these reagents are produced from scrap metal of unknown provenance. Electrocoagulation has been around for a number of years, but its limited application reflects the serious disadvantages faced by this technology. It requires that the whole of the treatment flow passes over the steel plates within the generator. This means that for flows of any size, a very large footprint is required in order to have the capacity to treat that flow. The fact that the treatment flow has to pass over the steel plates within the electrocoagulation generator means those plates are susceptible to fouling, and as a result, it is difficult to control the level of reagent being produced. Moreover, the very fouling of the electrodes will give rise to toxic byproducts unless those plates are maintained in very good condition, and this therefore has significant implications for the maintenance requirements of these units and defeats their advantage of being able to be deployed in remote unattended locations. AMS's innovation in the design and development of the SafeGuard H2O reagent generation system is to combine the advantages of both the use of ferrous as a treatment reagent with the technology found in electrocoagulation, whilst at the same time avoiding the disadvantages of both systems. And so essentially we are generating on-site a very concentrated solution of ferrous ions, which can then be applied to the treatment process itself. So the generator, which is not now part of the flow system, as is the case with electrocoagulation, generates on site a highly concentrated solution of ferrous, which can then be either stored, and I'll come to the benefits of that later, or used directly and injected into the flow stream, which then passes to a clarifier, where the reaction between the ferrous ions and the phosphate produce a sludge, which is deposited at the bottom of the clarifier for subsequent removal. And the clear fraction, now with a level of phosphate which is not prejudicial to human health and the environment, can then be discharged. And the whole system is monitored by an online phosphate analyzer. A small side stream of the treated effluent is then recycled into the generator, into which the concentrated iron, which is generated by electrolysis, is dissolved before the cycle repeats itself. SafeGuard H2O has a number of very important features. The first of this is that it is fully automated, making it ideal for unattended and remote locations. The reagent are generated on site, which also eliminates the supply chain issues that have dogged the industry. And because the reagents can be stored, this provides not only redundancy, but also enables the system to operate with either off-peak electricity or renewable energy resources. It is an extremely compact system with a footprint many times smaller than electrocoagulation, and incorporates real-time monitoring, which provides for remote control, particularly of unattended sites. The system incorporates a fully automated electrode regeneration system that ensures the electrodes are constantly in peak condition and therefore generating ferrous reagent in a totally predictable and controllable fashion. One of the features of the industry in which we operate is that there's a need to demonstrate and validate new technologies. But this often comes with a very substantial cost, either for the vendor or the client. And we've addressed that barrier to entry by designing a pilot unit that is very rapid to deploy at minimal expense. This pilot unit can treat between 1 and 2 cubic meters an hour. It's very small, but this technology at the same time can be scaled using the same components of a power source, control panel, the reagent generator, obviously much larger in a full scale, and then the necessary fluidics, pumps and so on to deliver the reagent. This can be scaled to very large water treatment systems. There are 2 criteria which any innovation in the water industry, or any other industry for that matter, must satisfy for them to be successful. The first of these is that the innovation addresses a serious problem. Phosphates in wastewater streams is a serious problem with very negative consequences for human health and the environment. And this innovation addresses that problem very effectively. The second is that this solution should represent a quantitative shift in the cost of solving for that problem. And this table demonstrates that. On the left-hand side, you have the range of chemistries that can be used to remove phosphates, with ferric chloride being the predominant solution. The second column is based on stoichiometric analysis of the amount of the reagent required in order to remove 1 pound of phosphorus. The third column is an estimate of the current cost of those reagents. Now that is based on an average, undoubtedly according to size and location. Those numbers will vary, but this is an indication of average costs. And from that we can derive the cost per pound of removing phosphorus. And you can see in this table that that represents here a significant shift in the cost of removing phosphorus using the SafeGuard H2O system. So to summarize, our technology is both affordable and effective. It generates a non-hazardous reagent in an environmentally sustainable manner. It's fully automated and includes real-time monitoring to ensure that the effluent that flows from the treatment system is always within regulatory limits. Increasingly, utilities are focused on their carbon footprint. By being able to use low power electricity, storage, this offers the opportunity for electricity load balancing, the use of off-peak electricity, as well as renewable energy resources. And it eliminates the transportation of bulk chemicals. It also eliminates the supply chain risks that we've experienced in recent time, as well as the health and safety risks associated with handling toxic hazardous ferric salts. Now this system can be either part of a greenfield investment project, or it can be used to retrofit an existing treatment system by simply eliminating the delivery of bulk chemicals by replacing that with an on-site generator of a highly concentrated form of ferrous, which is the active reagent within those ferric salts. And by using a certified precursor, steel, the provenance of which is known as opposed to scrap metal, we are producing a reagent free of contaminants found with ferric salts. We have two business models. The first of those is that the system can be purchased and then an annual fee paid for the consumables of that system and its maintenance. Alternatively, to put us on a par with current reagent purchasing regimes, we can price the system based on the volume of water treated. So it becomes not a capital and operating cost, but a pure operating cost for utilities, directly comparable with the cost of buying bulk chemicals from a bulk chemical supplier. As indicated earlier, we are fully cognizant of the need to demonstrate this technology. We have pilots underway, but undoubtedly more would be helpful in terms of demonstrating the effectiveness of the system and widening awareness. So if there is a utility or engineering group which wishes to see this system demonstrated and validated, we will happily engage with the understanding that the results of this demonstration pilot are well documented and communicated so that the broader market can become aware of this innovative technology that is addressing a major problem in a highly cost-effective manner.